All right, in this video, we get into chapter 4. We start with 4.1, probability density function. So before getting into the definition of probability density function, let's take a look at this graph here. So if I gave you a graph of function, let's see, this is a graph of function called f of x, and I want to find the area, the shaded area here between a and b end of the curve. So the area is equal to. So I believe that you would say something like this from your previous calculus class. If we want to find out the shaded area under a curve, we want to do the integration. We want to integrate this function f of x over the given interval a to b. So the area, the shaded area over here would be equal to integration from a to b f of x dx. And this is how to find the area, the shaded area between a and b here. And same thing, if we want to find the probability that x is greater than or equal to a less than b, that would be equal to the area and the density curve between a and b as well. Why was that? Because we know that if we want to find the probability between a and b, we want add all of the probabilities between a and b together, right? So since there are infinitely many possible values between a and b because it's continuous. So instead of doing summation, we're going to do the integration here. So the probability x is greater than or equal to a less than or equal to b is going to be equal to integral a to b f of x and dx. And this is one of the main differences between the discrete random variables and the continuous random variables. So for the discrete random variables, we know that if we want to find the probability of the interval, we usually do the summation. Okay, because the number of possible values between the interval for the discrete random variables is finite. So what we need to do and we can find the probability of each point directly from the given PMF. So we just add them all up. But if we're working with a continuous random variable, there are infinitely many possible values between a and b. So instead of doing a summation, because we cannot do the summation like mathematically because there are infinitely many possible values. So instead of doing summation, we're going to do the integration here. So I wish this is clear for you because I think it is clear to you because you all have finished the calculus classes as well. So if this is clear, let's take a look at the definition of probability density function. Let x be a continuous random variable, then the probability distribution or probability density function PDF. So this is shorthand version of the probability density function, which is PDF. So for continuous random variable, we have PDF. And if it's discrete, it's going to be PMF. Don't be confused, okay? Then a probability distribution or probability density function of x is a function f of x such that for any two numbers a and b with a is less than or equal to b, then the probability that x is greater than or equal to a less than or equal to b is going to be equal to the integration of f of x over a to b. So which is exactly the same thing as what we saw up here. That is, the probability that x takes on a value in the interval a to b is the area above this interval, and under the graph of the density function as illustrated in figure 4.2, which is the one shown up here. And the graph of fx is often referred to as the density curve. So we call this curve as density curve. Okay? Now all right, that's pretty much about the definition of the probability density function. And here's a little tip I would like to mention. I think I have mentioned this already before, which is that I'm sorry. Let me clean this real quick. That's the probability for continuous random variable. For continuous random variable, the probability of a single point, let's say c, is just a random constant number, and the probability x is equal to constant number, which means so we're looking for the probability of a single point. This is equal to 0. And I think I mentioned this before when we learn how to determine the discrete random variables and continuous random variables before. And actually, we can prove this by using definition here. We know that if we are looking for that the probability x is greater than or equal to a, less than or equal to b, we do the integration over a to b. So over here, since a is a single point, that means we want to integrate this f of x all over this one point, which means this is equal to integral from c to c, f of x dx. And based on the calculus you learned before, the integration over one single point is equal to 0. So this is always equal to 0. So always keep this idea in your mind. Yeah, if you want to find a probability of a single point, something like this. First of all, you want to say if this is a discrete random variable or continuous random variable. If this is a continuous random variable, you don't have to worry about anything else. Just put 0 over there, and you will get a full credits. That's for continuous random variable, okay? Because the probability of a single point of a continuous random variable is always equal to 0. If it's a discrete random variable, you just you need to do the calculation based on what we went over previously. Okay. And if this is clear, since we know that we don't have to worry about the probability of a single point of a continuous random variable because it's always 0. So this thing here would be equal to, which means we don't have to worry about the boundary points over here. In other words, we don't have to worry about if we have equal sign over here or not, because the probability of a single point is equal to 0. So this would be equal to the probability of x is greater than or equal to a, less than b, and this is equal to the probability of x is less than greater than a, less than or equal to b. And this is also equal to the probability that x is greater than a, less than b. So anyway, so we don't have to worry about the boundary points or the equal sign here, because the probability of a single point is always equal to 0 for a continuous random variable. All right, always keep this idea in your mind. Once this is clear, let's take a look at the property of the probability density functions. And for f of x to be a legitimate PDF, it must satisfy the following two conditions. Number one, f of x for all x is greater than or equal to 0. Why? Because f of x or PDF represents probability. For being a probability, it must be greater than or equal to 0. Okay. Number two, integral of f of x over negative infinity positive infinity is equal to the area and the intergraph of f of x, as it is equal to 1. So actually, since we are integrating f of x on the whole number line from negative infinity to positive infinity in general, that means we're adding all the probabilities together. Okay, so based on the property of distribution, based on the property of the probability distribution, we know that the sum of all probabilities is equal to 1. And that's why we have 1 here. All right. And of course, this is in general from negative infinity to positive infinity. In some different problems, it will give us some specific intervals. Okay. Now, let's take a look at this example here. And this is coming from the textbook, example 4.4. And I don't want to read over the whole background information here, but what we know is the possible PDF for x is this. Okay, f of x is the PDF of x. So f of x over here is equal to 1 over 360. It's a constant number for all x values between 0 and 360. And f of x is equal to 0 otherwise. Now, we want to do some calculations for here. Number one, we want to find the probability that x is greater than or equal to 90, less than 180. How to do that? So based on the definition we went over here, so if we want to find the probability of interval of continuous random variable, we need to integrate the PDF over this interval here. So over here, we're going to do the integration from the lower bound would be 90 the upper bound would be 180. Okay, f of x dx. And we know that the interval 90 to 180 is in the interval 0 to 360. Okay, so we can do the integration from 90 to 180 directly. And then we just do the integration, just plug this function back into here. We're going to have the integration from 90 to 180, 1 over 60 dx. And this would be equal to, we know the integral of 1 over 60 would be 1 over 60x. And then from 90 to 180. And this would be equal to 1 over 360 times 180 minus 90. So which is 90 over 360, which is 0.25. And that's the answer of this part. The probability that x is between 90 and 180 is equal to 0.25. That's section 1. Section 2. We want to find another 3 probabilities. One is a probability that x is greater than 80, less than 180. And then we want to find the probability that x is greater than or equal to 90, less than or equal to 180. And then we want to find the probability that x is greater than 90, less than or equal to 180. Right, so we want to find those 3 probabilities. So of course you can do the calculation here, but we don't have to, because we already have the probability that x is greater than or equal to 90 but less than or equal to 180 already, and we know that the boundary point wouldn't matter. So those 3 probabilities would be equal to that. Would be equal to the probability that this interval here greater than or equal to 90, less than 180. And they're all equal to integration from 90 to 180 f of x and dx. So which is equal to 0.25 as what we got here. So those 4, 1, 2, 3, 4, those 4 probabilities are completely equal to each other for a continuous random variable, because once again the probability of a single point of a random variable is always equal to 0. So we don't have to worry about if we have the equal sign here or not, because it wouldn't change anything. All right, number 3. What is the probability that x is equal to 90? So since this is a continuous random variable, right? This is a continuous random variable. And we're looking for the probability of a single point. What is it? It is 0. So what I want to emphasize over here, this is not equal to the function value of f of 90. Okay? If you want to find the probability of a single point of a continuous random variable, this is always 0. You cannot just plug the 90 back into the function here. You cannot do that, because it's a continuous random variable. If it's discrete, you can do that. That's how you find the probability of single point. You just plug it back into the PMF. You just plug the number back into the PMF and you will find the probability of single point. But since in this case we're dealing with the continuous random variable, so the probability of single point is always equal to 0. Okay? All right, number 4. What is the probability that x is greater than or equal to 0, less than 360? So actually, if you want to do the calculation, you just go back to the definition, just integrate the f of x over 0 to 360. But actually, since this is a kind of special here, this interval, because this interval 0 to 360 covers all the possible values of x. So which means we're looking for the sum of all probabilities of this random variable. So this would be equal to 1 automatically, because this interval covers the interval of all possible values of x. Of course, you can do the calculation. If you do the calculation, you'll get the same thing. All right, that's pretty much about the subsections of this problem. And before we move to the next definition, I would like to take a look at the graph of this function here. So we know that if we want to graph this is a function f of x, first of all, the possible values of x are 0 from 0. And let's see, this is x and this is f of x, okay? And 0 here and 360. 360. We use the open circle for 360 here because we don't have the equal sign, and we need a solid point. We need a solid point for the 0 because we have an equal sign for 0 here. And then we know the f of x is constant number, which is 1 over 360. Let's see, this is somewhere over here, 1 over 60. And of course, it's going to be a horizontal line like this from, this is a horizontal line, okay? From 0 to 360. And we can tell that the area of this rectangle would be equal to the width times the height, right? So 360 times 1 over 360 over here would be equal to 1. So the height times the width is equal to, the area of the rectangle is equal to the height times the width, which is 1 over 360 times 360, which is equal to 1, okay? Of course, we know that I think we say something like this before, and this kind of distribution is called a uniform distribution, which means that if the PDF is a constant number, or the probability of each point is exactly the same thing, we call it uniform distribution. And we know that the area of this rectangle is the sum of all probabilities. So this is always equal to 1 because the area of this rectangle represents the sum of all probabilities, which is equal to 1. So in other words, if in the future we have already know that the area of the rectangle, if this is a uniform distribution, if we're dealing with a uniform distribution, we know that the area is always equal to 1 because it represents the sum of all probabilities. And if we know height, we can calculate the width. Or if we know the width, we can calculate the height. Okay? And we're gonna say something like this later, okay, in this video. All right, so once we know this idea, let's take a look at let's take a look at the exact definition of uniform distribution. So a continuous random variable x is said to have uniform distribution on the interval a to b if the PDF of x. So of course, the a and b are the two parameters here. It could be any constant numbers for different uniform distributions. So the f of x, the PDF of fx is equal to 1 over b minus a. So basically, if you know the interval of the uniform distribution, you can find the PDF directly. Now let's take a look at how we get this PDF. So first of all, since we know that the PDF of a uniform distribution is just a constant number, right? Now, if we know that the interval is a to b, let's say a is somewhere here, b is somewhere here. And we know that f of x is a constant number and it's a straight line between a and b, right? And we know that if this is a uniform distribution, that the area of this rectangle is going to be equal to 1, okay? Let's say we know the height of this rectangle would be f of x, okay? F of x is a constant number, which means f of x, which is the let me rewrite this to make it clear. We know for the area of the rectangle is equal to height times width. Now in this case, we know the height of the rectangle is f of x, which is a constant number, times the width. The width of this part would be b minus a. And we know that the area of this rectangle is equal to 1 since it represents the sum of all probabilities. So f of x, if we solve f of x, that would be equal to 1 over b minus a. Of course, x is greater than or equal to a, less than or equal to b. And if you want to put it in a like general form of PDF, this would be 0 otherwise. That's how we find the PDF of uniform distribution with a given interval here. And basically, that's how you find a PDF of uniform distribution, like always. Okay, once you have interval, you can find the PDF of the uniform distribution directly by doing this kind of calculation. It's very easy. Just always keep this in your mind. If you are dealing with a uniform distribution, the area of the rectangle is always equal to 1. And that's how you find the PDF of this uniform distribution. Okay, and now let's take a look at example here. I will say that X is said to have uniform distribution on the interval two to 5. Now, what is the PDF of X? So basically, based on we know the interval already, and we know this is a uniform distribution, and if we want to find a PDF, we know that f of x, that would be equal to 1 over, based on the definition of uniform distribution, that would be 1 over the right endpoint minus the left endpoint. So that would be, in this case, that would be 5 minus 2 is equal to 1/3. So if we put it in a general form, f of x would be equal to 1/3 x is greater than or equal to 2, less than or equal to 5, and 0 otherwise. That's how we find the PDF of a uniform distribution with a given interval here. All right. That's pretty much about the uniform distribution. Let's take a look at this example here, and this I think this is the very last problem of this section. So the background information is blah blah. I don't want to read it over. And what we need to do is this a PDF. Of course, since it's PDF, we're working with a continuous random variable, and we have that the PDF of x is f of x is equal to 0.15 times e to the negative 0.15 times x minus 0.5 for all the values x is greater than or equal to 0.5, and we want to find the probability of x is greater than or equal to 1. So based on the definition we went over just previously in this lecture video, we know that if we want to find the probability of an interval, so we just need to integrate the PDF over this f of x over this interval here. Of course, since x is got to be greater than or equal to 1, the lower bound is got to be 1. What about the upper bound here? The upper bound is all the way to the infinity, okay? Because it's x is greater than or equal to 1. And then what we need to do, just do the calculation here. From 1 to infinity, we bring the expression of f of x back into the integration, 0.15 e to the negative 0.15 x minus 0.5, okay, dx. And then we just need to apply the power rule here. No, not power rule. This I think this is called chain rule. Okay, negative e to the negative 0.15 and then x minus 0.5, and from 1 to infinity. Okay, and you should know something about the integration, some basic rules of integration. We will say a lot of calculations about integrations in chapter 4 and chapter 5, and if you are not familiar with that kind of thing, you get a kind of refresh yourself a little bit, but we wouldn't say something too complicated. We wouldn't say something like substitution or something like that. We're just use some basic rules of integration, and if you are not familiar, I wish that you can kind of review on it a little bit. Okay, and then we just plug the upper bound and lower bound back into this expression here. We're gonna have if we bring the infinity back into here, we're gonna have the negative e to the negative infinity. Okay, if x is infinity, so this whole thing would be infinity. Negative that would be negative infinity, and then minus, and then we just need to bring 1 back into there. Negative e to the negative 0.5 times 1 minus 0.5. Okay, so this would be equal to, since e to the negative infinity is going to be 0. Okay, so this first part is 0. And then 0 minus negative e to the negative 0.15 times 0.5 is going to be negative 0.75. So this would be, since we have minus, is going to be a plus. That would be e to the negative 0.75. If you type this whole thing in your calculator, that would be something approximately 0.928. That's pretty much how to find the probability of x is greater than or equal to 1 here. So the key point for this kind of question is, first of all, we got to know that if we want to find out if we want to find a probability of interval of a continuous random variable, we got to do the integration over this given interval, and then you need to know some basic rules of integration. Number 2, we want to find the probability that x is greater than or equal to 0.5. So of course, first of all, we want to think of the definition, which is the probability of an interval is going to be equal to the integration of f of x over this interval. In this case, that would be 0.5 to infinity. Of course, you can just do the calculation as what we did above here, but in this case, we don't have to, because, this interval is the exactly interval of x values, which means this interval covers all of the x values, and the probability over here we're looking for is the sum of all probabilities. So that would be equal to 1. Okay, because this interval is the exactly same interval as x has in the PDF. So you don't have to do the calculation here, just put a 1 here, because we're looking for the sum of all probabilities. Okay, and then what about number 3, the probability that x is greater than negative infinity, positive infinity? Of course, we want to think of that that would be equal to negative infinity to positive infinity, f of x dx. This is from the definition, right? So since we know that x starts with 0.5, and x starts with 0.5, if x is equal to any number less than 0.5, that would be 0. So we can that break this into 2 parts based on the property of integration. That would be equal to, let's say, negative infinity to 0.5 f of x dx, and then plus 0.5 to infinity f of x dx. We can do this, right, based on the property, the additive property of integration. And we know that if x is less than 0.5, the value of f of x would be 0. So in other words, we just bring 0 back into here. That would be equal to negative infinity to 0.5, 0 times d of x, and then plus 0.5 to infinity f of x dx. And of course, the first part would be equal to 0, right? The integration of a 0 is 0, and that would be equal to 0 plus the integration 0.5 to infinity f of x dx, which is exactly the same thing as what we get up here. So this is equal to 1. So in other words, the probability x greater than negative infinity less than positive infinity is exactly the same thing as x is greater than or equal to 0.5, because the possible values of x got to be greater than or equal to 0.5. All right, I hope this all makes sense to you. And there are 2 main points for this section. Number 1, if you want to find a probability of interval of a continuous random variable, you got to do the integration over the integration of the PDF over the given interval. Number 2, the probability of a single point of a continuous random variable is always equal to 0. Okay, And that's the main difference between the discrete random variables and continuous random variables. All right, that's all about this video.